All right, we're in chapter 3, two-dimensional kinematics, and we're finally going to start talking about two-dimensional kinematics. Um, so you kick a ball, right? You've got some arc that the ball goes through, and there is a vector that describes your displacement all along that arc. And you'll notice that vector points at different places at different times, right? It points at different places at different times depending on where the ball is. So the vector that we're talking about, S, points to where the ball is. Now, the way I've written things here, I used S because quite frankly, I get tired of X and Y. So here we go. This is S. It's a vector from here to wherever the ball is at time t. It has in it a vector v that's the initial velocity and a vector s that's initial position. Now, that's not. In this case, S naught is 0, right? There is no S naught. But this is in two-dimensional kinematics, we're looking at a constant acceleration problem. So because it's constant acceleration, this vector equation is exactly like, this is a shorthand, this is a quick and dirty way of writing two equations, or even three depending on how many dimensions we're talking about, right? This is a vector is the acceleration vector times time plus the initial velocity vector. Alright, so that just parses out. We could write that as its x components and its y components. Those are two equations. And all we've done is we've gotten lazy and we've written it as one by using little vector notation on top. Same thing for the position. Right? This looks just like x equals 1/2 at squared plus v naught t plus x naught, except these are now all vectors. And because they're all vectors, this actually represents three independent equations along each direction. Right? We can break it out and write it, right, as along the two different directions we're going to be talking about here, x and y. We can write it as two independent equations, right? Two velocity equations, two position equations. And so, just again, this and this are exactly the same thing. We have just simply written them more compactly in the first slide than in the second. Now, this is really the working space. This is the way we're going to use it most of the time when we're doing problems. All right, when we add gravity to the mix, we're going to talk about a lot of problems where the acceleration in x is 0. Right? There's no acceleration in x, which means we have constant velocity in x, but we're going to have gravitational problems. This is a projectile motion problem. We're going to have gravitational acceleration. So that makes our velocity vector equal to minus gt times the j hat, right? Plus whatever our initial velocity is. So that's the acceleration minus g times time, and that's in the j hat direction. In position, again, the only place, because we've decided we're going to work only problems where the acceleration in x is 0, the position. In the position, again, the only term that's left, right, from the acceleration term is the gravitational acceleration in the j hat direction. All right, so that's our little equation written as 1. When we write it out as separate components, right, for the I hat direction we have the x equations, and then again, it's constant acceleration in x, so, no acceleration in x. So Vx is always whatever the initial velocity in x was. And then position in x is just linear with respect to time, right? Because there is no t squared term because the acceleration in x is 0. In y, we have this minus 1/2 gt squared plus v naught yt plus s naught y, right? We've got our little second order polynomial for y goes as t squared, and then the velocity in y has this term due to the acceleration of gravity minus gt. So when we try and look at this, right, and we have an initial velocity that we are given in terms of a magnitude and a direction, how does that break out? Well, we're given the magnitude 30 meters per second. We're given the direction at 45 degrees. that means the x component, right? The x component, if this is if we were to draw our velocity, right, at 45 degrees, right? So the x component to here is the cosine of 45 degrees times 30. The y component in that direction is the sine of 45 degrees times 30. So the x component is the cosine times 30. The y component is the sine times 30. The better way to think of it is the adjacent component is the cosine times 30. Cosine of the angle times the magnitude. The opposite, all right, component is the sine of the angle times the magnitude. And keeping that in mind when you do this is because sometimes the angle might switch between what our reference is, and it might not be x and y cleanly like this. So here we are, our position x, 30 cosine times 45, and that's in meters per second, times time plus 0 because we have our initial position x is 0. Position y, minus 1/2, 9.8 meters per second squared times time squared plus 30 sine of 45 degrees meters per second times time. So this is our set of equations that describe where, and this is for the 45 degree one, so that's the red line. We're looking at 30 meters per second, 45 degrees. That's that little red arc right there, right? That is this SX and SY describe where you are along that at all times. When does SY equal 0? So what does it mean when SY equals 0? Well, that means you're back at the ground, right? So if we look at the equation for SY, we're always asking in projectile motion, when do you hit the ground? All right? So here's the equation in Y. Well, there's a trivia answer. When do you hit the ground? Well, time t equal to 0. You're on the ground. All right? Yes, that's correct. You start off on the ground. That's the uninteresting answer. All right? So when is the next time you're on the ground? This is an equation. This is a question we ask all the time in projectile motion. When do you hit the ground? Not when you started out, but later. When do you come back to the ground? And so we just solve this equation for time, and we can figure out how long, right? How long this projectile is going to be in the air. This is how long it's in the air. Why did I say that? Well, I haven't said anything about x on this, right? But y determines how long it's in the air. There's no acceleration in x. Just the y component determines how long it's in the air. So it goes up and it comes down, and at 4.3 seconds, it's back on the ground. There's another thing here in these graphs to point out. See this vector, these are all the same velocity, 50 meters per second, at different angles. All right? So 15 at 50 meters per second at 15 degrees ends up here, and 75 degrees, it ends up at the same spot. If you want, if you want the longest you can actually send a projectile, it's at 45 degrees. All right, so as you take the angle below that, you drift back this way. As you take the angle up from there, it drifts back this way. It's symmetric around 45 degrees. At symmetric angles around 45 degrees, you land at the same spot in projectile motion. So what happens in x all this time while we go up in y and come back down? Well, we just put in the equation for x. We now know how long we're in the air. How far did we go? We went 91.3 meters. Slightly different from what they have in the book, but it's rounding at some point, right? 91.3 meters. All right, last thing, and we're going to talk about the addition of velocities. And this will be it for this chapter. So when we add velocities, and we'll be talking about adding velocities all the time, there are different ways to think about this. All right. So the total velocity of the boat with respect to the shore, and here we go. We've got a velocity of the boat with respect to the water, of 0.75 meters per second straight across. We've got a velocity of the river with respect to the shore of 1.2 meters per second this direction. Now, it's important to think about how I said this. We have the velocity of the boat with respect to the water, the velocity of the water with respect to the shore. If we add those two, we get the velocity of the boat with respect to the shore. All right, so we've got V boat, oh, that's terrible, V boat to water, right? Water. The velocity of the boat with respect to the water. No. All right, let me just say it again. We have the velocity of the boat with respect to the water. We have the velocity of the water with respect to the shore. If we add those, we've got boat to water, water to shore, we end up with boat to shore. The velocity of the boat with respect to the shore. Whenever you are working these addition of velocity problems, it's important to think in terms of velocity of this relative to that, velocity of that relative to that other thing, right? So in this problem, the question is, what's the velocity of the boat with respect to the shore if the boat heads straight across the water with respect to the water at 0.75 meters per second, and the river is flowing at 1.2 meters per second this direction? So we've got a J component, we have an I component. We add those. Notice you still got a J component and an I component after you add them, right? It's not 1.2 plus 0.75. It's 1.2 I hat meters per second plus 0.75 J hat, right? You have to remember that these are vectors and they have components. And then you get the magnitude of 1.42. You get the angle, all right? The angle 0.75 over 1.2 or 32 degrees. All right, that's it for chapter 3.